Hello, everyone, and welcome to Lab Manager's Safety First webinar series. My name is Catherine Crawford-Brown, and I'll be moderating today's discussion, which will focus on planning, testing, and working safely in a fume hood. We like our webinars to be very interactive, so we encourage you to send us your questions at any point during the presentation. Our speaker will address these questions during a question and answer session following his presentation. To ask a question, simply type your query into the question box, which is located on the left-hand side of your screen. We'll try to address as many questions as possible during our time together. If we happen to run out of time, I will forward any unanswered questions to today's speaker. He can respond to you directly. Just a reminder that this webinar recording will be available on demand immediately following this live presentation. With that, I'd like to introduce our presenter for today's webinar, who joins us from LabConco. Nathan Richardson is a project development manager at LabConco Corporation, a 94-year-old laboratory equipment manufacturer with specialization in ventilation and biological safety equipment projects across the United States and Canada. As a molecular biology researcher and lab equipment industry specialist for 8 years, Nathan has practical experience working within fume hoods and biological safety cabinets, has assisted architects and engineers in laboratory ventilation design for new construction and laboratory renovations, provided on-site and regional laboratory safety training, and develops best practices reference material for fume hood and biological safety cabinet applications. Nathan, thank you for joining us today.
Thank you, Catherine. It's great to be here and have a conversation with all of our guests about safe science. We're going to look at planning on how to design a lab a little bit more efficiently and picking the right hood for the application, testing procedures both on the front side for development of fume hoods and standards, and then during installation, and then the continued testing to make sure that equipment is working properly. And then probably the most important piece is working safely inside of the fume hood. So thank you all for joining. I hope this is entertaining as well as educational, and we will continue right now. So I'll give you a quick view of the agenda. If I can get the tab, there we go. All right, so as I said, planning for safety. There's organizations that basically give all of us manufacturers guidelines to follow so that you know you're working inside of a piece of equipment that is going to protect you from what's going on inside. Hood type is based, like I said a moment ago, on the applications that are being done within the hood. So we'll discuss some of the different options that are available there to ensure that you're choosing the right type of equipment to meet those needs. And then some of the design features for building a new lab, or if there's a renovation being done or a hood replacement, and looking at some of the aspects that go into where to place hoods. Testing for safety, we discussed those a moment ago, and you can read the slides. And then using and maintaining fume hoods. Operating safely is key, but there's also some maintenance factors and some alarm protocols that we want to review to ensure that everybody is safe and working properly. All right, so ventilation organizations, these are the companies and organizations that provide standards and recommendations that fume hood manufacturers are going to be following so that we can produce a piece of equipment that meets safety guidelines based on a variety of parameters. And in the world of acronyms, each one of these organizations has a pretty long name and then is shortened up by a quick acronym. And they all have different focuses, and some of them are overlapping. As we can see, all of those acronyms then turn into guidelines that have specific pieces to them. So when you're developing how you want to create a safety program or looking at different pieces of equipment that you want to purchase for a new laboratory or renovation or adding to existing space, these are some of the guidelines that can help you choose which manufacturer to purchase from and ensuring that the manufacturer is meeting those safety standards prior to even evaluating the equipment once it's installed. So these give all of our clients the ability to evaluate and have peace of mind knowing that there are organizations dictating what manufacturers are required to do so that you have the safety that you need for when your technicians are actually working within the equipment. So getting onto the selection. So before you even put a fume hood into place, there's a variety of options that you have. So as we mentioned, the application is really what's going to dictate what type of equipment you need, the type of protection that's required. There are known and potential hazards. In certain labs, there's going to be repeatable processes that give you the opportunity for one type of hood. Other labs are going to be R&D and have a variety of chemicals and different applications, so perhaps a different type of hood design is required. And then operational considerations need to be addressed. Equipment size is an important piece, and making sure that the location of that equipment within the hood itself, there's some guidelines on how to do that we'll discuss a little bit later on, dealing with the safety of usage with equipment. Proper location, which ties into the design. We'll touch bases on exhaust systems and some of the benefits and drawbacks of the various types. And then some of the accessories that are going to be necessary for different applications that are required depending on your laboratory and the type of research that's being done. So on the pictures to the right, on the left-hand side picture, those are actually filtered fume hoods. So those would have addressed the repeatable processes that I was talking about a moment ago. The upper right picture shows you some demonstration style hoods, which are often used in classroom laboratories. So a professor can walk along a row and see what the students are doing and reinforce those safe practices. And then the bottom right is more of your standard type of fume hood that's going to have a variety of applications, ducted out, and has, you know, the features that each lab is going to need and be created to meet the lab's needs with different fixtures and different types of capabilities depending on what the requirements are for that laboratory. So we get into selecting the right type of safety equipment. So we're going to need an enclosure. So if it's biological, we typically go to biological enclosures. This webinar is focused on fume hoods and ventilation, so we're going to go down the chain from there. And again, application is going to dictate the needs. So perchloric acid has some concerns that are unique to the lab environment. So that's one of the first things we want to ask when we're trying to help a client determine what type of hood they want. And usually perchloric acids are digested, so we need to know the heat so that we can determine whether or not a PVC, which is polyvinyl chloride, or it's a plasticized type of hood, or stainless steel is going to be appropriate. There's some other factors that go into that. So, a sales rep or an architect may want to have a deeper conversation with the end user or the lab manager on exactly what's going on inside of that hood. Perchloric acids aren't used. Another chemical that's relatively frequently used, especially in etching processes with metals, is hydrofluoric acid, and that has some unique characteristics. So then again, we ask the heating question, and then the different options that we have. And you can see on the right, it says Lexan Sash. We'll get into that in a little bit further on in the slides. But each one of these hoods and those enclosure designs on the right have unique characteristics that are there to help deal with the application. And RI is the acronym for radioisotopes. So it's going to be welded corners. They're going to be use of lead bricks. If lead bricks are going to be used, that's added weight. So, there's these additional follow-up questions based on how these pieces of equipment are being used to validate what type of specialty items may be needed, or if a standard hood is the right purpose. And then we get down to the bottom. And while this isn't very safety related, it is cost related. Interested in saving money and using ducts for high performance, VAV, which is variable air volume, or if there's not ducting capabilities, we can get into ductless carbon filtered enclosures. So to touch bases on some of those quick hoods that we talked about, the liner type is important, especially depending on what types of applications are going to be used. Corrosion will destroy metal liners. Also, there's dissolution. We've got melting processes. So that's why that heating question was important on the previous slide, because if somebody is using a hot plate and then they place a beaker onto a PVC or polypropylene type hood, that plastic starts to melt and now they have disfigurement within the hood and it causes problems. So those questions need to be addressed. And there's also some factors that can be taken into consideration. If a customer does need a polypropylene or PVC style hood, but they'll be doing heat, adding some type of heat resistant plate inside so that they can place the beakers off of a hot plate. So again, liners are an important factor when we're trying to determine what type of hood is going to be the right choice. So the most common liner materials are fiberglass reinforced panelized composite, or FRP, polyester blend, also molded fiberglass, which does not have any seams, so you're going to have great resistance to corrosion over the longevity of the hood. Epoxy coated steel is a light application usage. Again, steel is going to corrode, so if there's acids or solvents that degrade metals, it's usually not the best choice for the long term. In the short term, they will hold up. Stainless steel's usually in some type of specialty acids, and then that's what that radioisotope hood that was previously mentioned. And then you've got your two plasticized types of hoods, polyvinyl chloride and polypropylene, again for specialty acids. So to highlight a couple of these, general chemistry is going to be your FRP composites, frequent acid use, something that's molded that does not have seams for degradation because that can cause problems over time. And then infrequent use is a lower cost epoxy coated steel type. And then we get into the large volume acid digestions, usually go with the polypropylene or the PVC styles. Again, they're going to be molded, so you're not going to have seams for degradation. But they also have washdown systems because we're not only talking about the safety within the laboratory, but there's also a safety factor of the ventilation of fumes that are going to be leaving the building and making sure that those are properly handled and that the volumes meet the requirements of safety standards for the county, city, and state. And then perchloric applications. So perchloric salts have the possibility of becoming explosive from friction, heat, force. So those systems have washdown throughout the entire ventilation, which requires the duct work at every interval around corners to have water streaming down to wash away those salts so they don't become volatile and dangerous. And then radioisotopes, obviously, there's going to be additional safety items within the hood because the hood itself isn't going to be protecting from the emittance of all different types of radioisotopes. So uncommon applications for most labs, but need to be addressed on the front side so that the wrong decision isn't made and we're having to waste money and cause potential safety hazards. And from the first slide that we got into, we touched back on them. So these organizations are the ones creating specifications on what we need to make sure that your hoods will meet safety requirements so your technicians are safe. And as you can see, we've got UL and NFPA, so there's a variety of these. And again, as we touch on creating standard operating procedures, these are the organizations that can help with determining how you want to build your operating procedures. And it just gives you peace of mind knowing that they hold us as manufacturers to a standard, and you can dictate that you want these types of listings on the piece of equipment that you purchase. With a specialty safety glass, this is where hydrofluoric acid comes into play. So most fume hoods will have a tempered glass, or it's also called toughened glass, or will have a laminated type of glass. So the main difference between tempered and laminated is tempered, when it shatters, breaks into small pieces, and laminated glass is sheet glass that's adhered by a layer that holds it together. So both of these have benefits and drawbacks. Tempered glass has greater resistance to force. Laminated glass does not shatter in most cases without a really astronomical amount of force. And then polycarbonate safety glass is used for the hydrofluoric acid applications, because hydrofluoric acid will etch both tempered and laminated glass in a relatively short period of time with not a whole lot of volume. So the safety issues, as you can see in the picture on the right, you can't see through a glass that has been damaged by hydrofluoric acid usage. And then you have a maintenance safety issue with trying to replace that, because most hoods are put up against walls and oftentimes side by side with other equipment. So there's additional safety issues. But each of these are types of glass do go through the same type of standards process to make sure that they are safe for use within laboratories. And then other pre-purchase safety considerations that need to be made is, does the lab require an explosion-proof fume hood? And does the equipment going into the hood, is it going to be the right size hood for that equipment and that application? Can you work within a ducted hood, or can it be a recirculating type? And are ADA considerations being met to ensure that if you have an individual who has restrictions, they have the capability of still doing research and using the equipment? So these are just other things that need to be taken into consideration. So to quickly touch on explosion-proof hoods, basically it's void of any spark potential, removing any electrical components from the hood, putting in explosion-proof type lighting fixtures, and then on site is where all of the electrical is connected to meet individual state and local codes, because they're different at each area. And there are certain limits that are required to meet classifications for explosion-proof hoods. The first being the Class 1 Div 1 type of laboratory. So this is explaining a type of place, space such as a room, or it can be considered the fume hood itself as that type of designation, and it can be compounded. One can be Class 1 Div 1 within a room that's Class 1 Div 2. So there are some unique characteristics to these. An NFPA 70, which is the fire protection agency that gives the standards for a lot of the fume hood equipment, they're showing lower explosion limits of 25%, and then NFPA, the Series 45, talks about unusual hazards. So unusual hazards are exceeding that 25% lower explosive limit, and then there's a calculation of a dilution factor, and then comparing it to the air volume that's going to be consumed by the fume hood itself. So there's some various reasons why an explosion-proof hood is needed, and these are those reasons. Most frequently, they're unnecessary unless these specific reasons are being met, or a state code requires it based on the application. So there are some things that need to be done on the front side to determine whether or not this type of specialty hood is required. Choosing the right size hood, again, an important aspect, because in equipment, airflow, lab space are all going to be important. And fume hoods come in a wide variety of sizes. As you can see, the picture on the left is a 3-foot fume hood. Not very big, but oftentimes there's not a whole lot of room needed in a fume hood in certain labs. Alternatively, on the right, you've got a much wider fume hood that's floor mounted and has additional height, because the equipment inside required that type of size configuration to meet the needs. So choosing the right hood is a safety factor, because you need to make sure that you're maintaining the proper ventilation. And if you've got really big equipment and too small of a hood, it's going to block that containment and cause problems. And then we touched on filtered hoods. So these are usually during applications that are repeatable. Multiple layers of filtration if it's considered a filtered fume hood, or DH3, according to CIFA 9, another one of the regulations that we have to meet. And really, if you're going to be choosing a filtered hood, you want to ask yourself if there's going to be certain applications being done, the type of construction that's required. A lot of heat isn't really great within filtered fume hoods. There are certain types of chemicals that are not appropriate. So again, it's on the front side making sure we're meeting the safety factors, so on the back side you've got the right piece of equipment. And then ADA compliance. So if you've got an individual who has restrictions, making sure that there is a hood that's designed to meet those needs. So Perhaps it's lowering the height of the hood itself, putting in lever handle fixtures as opposed to something that requires a grip, having the electrical duplexes within reach. So these factors all need to be considered for the safe use by a technician that would be restricted in one way, shape, or form. And then the design factors get into safety as well. So if we talk about the type of air volume systems that are used in these types of applications, where to place a hood, how a room is pressurized, the direction of airflow, and exhausting. So there's two main types of mechanical system, constant volume and variable volume. And they mostly are dependent on the size and scope of the project, but also sometimes due to applications. And constant volume means that the total volume of air does not change regardless of how the sash is positioned. As long as the hood is on, it's sucking air. In a variable air volume system, as the sash moves, there's a sash sensor that gives feedback that modulates the airflow. So the face velocity will be maintained, the volume will be different. On a constant volume system, the volume is maintained and the face velocity differs depending on the sash position. We'll get a little bit more into that here shortly. Ideal hood placement. So airflow is turbulent and it doesn't have much density. So having the hood as far away from an airflow corridor, away from walking areas, and having air supply registers pushing air down into the room and not towards the fume hood. So putting in a block register if there's a diffuser up close to where the fume hood is. So again, not often do we always have the ability to design our laboratories, but if we do have that option, trying to keep the fume hoods away from any type of movement of air that would create turbulence and disrupt the airflow and restrict containment, which is what we're trying to avoid. So as you can see in the picture, there's a handful of hoods along a back wall. You've got diffusers pushed out away from the fume hoods themselves. The one drawback to this would be that those adjacent doors to the exit by the one fume hood on the left. Outside of that, this design is pretty great. And you can't always be perfect on where you're going to design and place hoods because there are requirements for a certain amount of hoods in laboratories, and space only has so many options to be developed. And in retrofits, you put them where you can. So there's options on placing them in certain places when you can, but if you can't, you might just have to address things on a case-by-case basis. Room pressurization. Typically, fume hoods are placed in laboratories that are going to have a negative pressure, which is annotated on the bottom, which means the exhaust volume is going to be slightly greater than the supply volume going into the room. Positively pressured rooms means that there's going to be more supply volume, and you've got the potential to put laboratory air into open spaces, which is typically wanted to be avoided. And then a balanced room is keeping things equal, which is challenging to do because there's a lot of leakage in and out of rooms at certain areas. But traditionally, your laboratory is going to be under negative pressure where there's going to be fume hoods. Just to give you an idea of how airflow works, velocity versus volume, we talked about this very briefly. So the velocity is the rate at which the air is entering the fume hood. The air enters through an opening, which is going to be your surface area. So you multiply your surface area, which is your sash opening area, by your face velocity, which is the airflow moving in, and that calculates out your exhaust air volume, which gets into the pressurization. So we've got a couple little drawings to help visualize how a constant volume system works. So if we've got 1,000 CFM exiting the fume hood at the top of the picture, you're going to have a negative air draw into the fume hood. You're positively pressurizing air through your supply that's coming through the bottom with the arrows and the green pluses. And then you've got an offset of 100 CFM towards the left at the door. So intermittently, that 900 CFM of makeup air will be supplemented by that 100 CFM of offset air coming through the door, which means the room is negative. We're drawing air in from the corridor to be exhausted where the hazards potentially would be within the fume hood. So it always is drawing air into the laboratory, which is the design that's most frequently desired. Variable air volume gets a little bit more complex. While you have the negative air draw going through the fume hood, when the sash is open, you'll still have this supply air system. And then there's a balancing of sorts because you're going to modulate the sash position, which will in turn change the volume of air that's leaving through the fume hood. So as we get to this next picture with the sash being closed, that airflow is going to be much more restricted through the fume hood. So that secondary general exhaust valve on the left-hand side of the photo is then opened up so that we can maintain that pressurization and maintain that volume of air being supplied and exited through the room to allow for the room to stay negative, but be able to move that sash up and down on a variable air volume system. This is a very simplistic view of this system. Traditionally, you're going to have quite a few fume hoods that are going to be working off this same type of system. So there's going to be a lot of air supply and exhaust air fluctuations, and these dampers modulate how much air is going to be moved through the hood, through a valve, through multiple rooms. So it's much more complex. This is, I want to say dumbing it down, but trying to make it a little bit more understandable on a small scale, even though these systems are traditionally on a much larger scale. And when we get to the safety aspect of it, directional airflow is key. So when you've got the hood running, you're going to have negative airflow going out through the exhaust system. It's going to create a negative pressure zone around the fume hood. You also have the secondary general exhaust, which is going to create a negative pressure system. This is on a VAV. As the sash modulates, that general exhaust is going to open and close. So you're going to continually have this negative supply air towards the right side of the room. Negative exhaust air. The supply air will be provided by the diffusers, which are located in this example on the left side of the room. So you've got a positive pressure system over there, and it's moving in a linear fashion from one part of the room towards the exhaust system. And as you can see, it's away from the corridor, away from the door. So it keeps the corridor safe for individuals who would be working there. Even if that supply air was overpowering the exhaust system in some type of circumstance where the exhaust wasn't working properly, you'd still be pushing the air, the clean air, towards where the contaminated air would be. So it's a safer design based on the way this lab is laid out. And to give you an idea of how these hoods actually work, so a constant volume system, you're going to have room air going in. When the sash is open through the sash opening, as you close the sash, there's going to be bypass air. The benefit of that bypass air on a constant volume system is that you've got a large volume of air, and if it still needs to find a way into the hood because it hasn't changed and the surface area has changed because the sash is closed, it needs a place to go without turning into a super negative pressure draw. And also, if the sash is closed and there's an application inside of the hood that generates heat or is still going on, it gives the ability to suck that air out through the ventilation system with still a pretty large volume, which is moving with a greater velocity than, let's say, a VAV system. Auxiliary air is a kind of an older type. The benefit is you're bringing outside air in to provide that ventilation source and maintaining that containment within the hood so that your technician is safe. The downside is when it's very humid and it's air conditioned inside, there's condensation that can form in the hood. Conversely, when it's winter time, there can be pretty cold temperatures inside of the hood. But theoretically, it's saving energy and still allowing for containment. Some design changes that came into play is reduced air volume. So now, similar to that constant volume, there's a restricted bypass at the top, which is going to reduce the amount of bypass air that comes in when the sash is closed, creates a greater static pressure up there. But if you did have a heating application, it does provide a block from that heat vortexing back out of the hood. So again, you're maintaining containment by adding a fixture within the fume hood to compensate for an open bypass. So you're reducing the volume necessary, but still keeping that containment safety standard that's being required. And then the advent of variable air volume really was an energy saver, but it also allows for constant face velocity, so the speed at which the air is coming through the hood. And when you're doing certain applications, that becomes very important, because in a heating application and you're shutting the sash on a constant volume system, you're going to be generating a much greater speed of air, so you're cooling your processes, so you're not able to function as efficiently. With a VAV system, if you had that same process, lowering the sash would have the same face velocity as having the sash wide open, so you're not creating those impediments to your application. And most large-scale systems are on a variable air volume system. So those kind of give you an idea of the types of systems and the layout. So testing for safety is what we'll get into next. And again, we go back to the standards. These are the individuals and groups that are creating the structure for manufacturers to follow, so that we can provide a piece of equipment that's safe and functional for you. So the two organizations that helped develop a testing parameter for fume hoods was ASHRAE and ANSI. So ASHRAE 110 in 2016 updated their requirements and how they do their test procedures, and it's a 3-part test. And it's not a pass-fail, it's just setting a standard based on an as-manufactured rating, as installed, and an as-used rating, with tracer gas containment, a flow visualization, and then a face velocity profile. What got compounded onto this was high performance definition, which is another organization called CIFA, and CIFA 1 defines high performance as 60 feet per minute with the sash opening at 25 inches, conducting that same test and giving an as manufactured rating, and then also an as installed, as used rating. And the aliases that are used are low velocity, high performance, high efficiency, all meaning the same thing. So this brings in a containment standard that we're trying to uphold, but reducing the face velocity, which sometimes causes unease based on the traditions of 100 feet per minute that have been established for many years up until these new designs came out. But the difference that came into play are how these fume hoods are designed to contain and be safe for usage. So we've got the stable vortex on the left and an anti-vortexing on the right, which allows for these lower volumes, lower velocities to provide a great level of containment because of the engineering of these fume hoods. So just to give you a peek at how ASHRAE 110 looks, on the left we've got the face velocity profile test, which is done at multiple points along the sash plane. And then you've got the visualization test on the right-hand side. And then we're showing the tracer gas, which gives the part per million containment of the fume hood based on those parameters. But what you'll notice here is that there's not a thing in the hood. Last time I worked inside of a fume hood, it didn't much look like the left, but more like the hood on the right, where there's a whole bunch of stuff inside the hood. Probably not that bad, but sometimes there's going to be equipment, there's going to be other things that don't give the same interpretation as the ASHRAE test does. So it's a good parameter, obviously, to start from, but knowing that there might be equipment or things inside of the hood that may adversely affect the airflow. So it's just a consideration to make when evaluating the velocity. NIH, the National Institutes of Health, came up with a little bit more challenging test where boxes are placed inside the hood, a larger volume of tracer gas, doing walk-bys and door movements to create turbulence within the room. So again, this just takes the ASHRAE test to another level, saying that, hey, we want to test this on more real-world type conditions, not just as a standard for high performance. So when you're developing what your standard should be, you can take into consideration the face velocity, how you want to test at different sash heights, how frequently you want the testing to be done, what criteria at which you want to have the hood tested, and then having an organization that will come out and certify this based on your requirements. And then over time you can evaluate to make sure that the way you have developed your standard is meeting your safety needs. And that's the most important thing, because if you're finding that they're not, then you get the ability to adjust them, by increasing the face velocity or changing where the sash position is. Part of that last process was selecting a certifier. So you want to make sure that they have experience, have done and are certified in ASHRAE 110, and going through and have references and getting quotes for your work to make sure that they know what they're doing, because it's your technician's safety that's at risk here if you have a certification organization that isn't experienced or isn't familiar with how fume hoods work. There should be a sticker on each of the hoods showing when it was validated by hood and at what face velocity along what sash opening, so that there's reassurance that it's been tested, is safe, and every year you validate that the last 365 days have been safe when you get that updated date. So traditionally, it's going to be on a yearly basis, but sometimes biennially and sometimes biannually, depending on the organization and requirements. Standard operating procedures are an important factor as well. So teaching your technicians how to properly use fume hoods, review the chemical risks so that you can determine if a certain hood needs a different assessment than another hood based on application or equipment. Consult OSHA for the chemical guidelines to see what their recommendations are. And user inexperience. It seems like creating a standard operating procedure based on somebody not knowing how to use the equipment will give them a much broader overview and understanding of how things should be done at your facility, versus having an expectation that they know what they're doing and not giving them enough detail. And then, installation qualifications, operation qualifications, the IQ, OQ. So when a fume hood comes in, having it go through a standard protocol before it gets used, and then your maintenance and recording schedule to ensure that consistently you're testing to make sure that that containment is still meeting your standards so that your technicians are not at risk. So training and protocols again, falls under standard operating procedures as new individuals come in, and having recurring training and going over how to use things, understanding airflow monitors, how to turn them off or silence them, what to do in a risk situation, checking to make sure that the certification is up to date. So just additional protocols and standards and training that can be done for technicians and for lab managers to ensure that safety is being upheld. Now we'll get into proper use. I want to reduce obstructions, so keeping things out of the way of the technician and away from the sash. So again, proper use is PPE. Work as far away from the hood opening as possible. The volatile chemicals that are being vaporized or in gaseous form are as far back as you can keep them, and don't lean against the sash, and keep your head and face behind the sash. So just good safe practices to maintain that safety, because the more you open the sash, the more movement there is, the closer you are to that sash plane, the more risk there is. Elevating equipment, keeping things up off the floor or on a bench top, keeping them up off the bench top a little bit. In the case of having some type of heating element or a furnace inside of the hood, you can see by the two pictures, there's a great difference on how that airflow dynamics works when you have a piece of equipment that's down on the work surface versus elevated a couple inches, so that you can get a clean sweep underneath the piece of equipment. It's also going to dissipate the heat better when you have that type of elevation. So equipment positioning is very important in maintaining the safety of your fume hood for your technicians. Working 6 inches inside of the hood, keep things back. The closer the equipment or applications are to the front of the hood, the greater the chances for some containment breaches. Fast arm movements can really impact how a hood contains. As you can see here, based on a shadow dynamic, that on the left, when you have your vapors really close to the sash pane, you're closer to your breathing zone. In this diagram also, it shows the sash completely open, which is not necessary based on this application, and it's not protecting the breathing zone. So now this individual is breathing, and moving their arms, which creates turbulence, which could potentially bring those hazardous vapors out into the laboratory space for a moment. Again, the second image a little further back, and then the third image all the way to the back. Now, of course, there's issues with reaching that far back and being able to actually do what you're supposed to do. So there's a little common sense, but this can all be addressed in the standard operating procedures and training of your technicians to make sure that they understand the risks that are involved with airflow interference. Keeping the sash as low as possible. I reiterate it and over and over again. If there's splashes, it's protecting the individual. If there's vapors being formed, it's keeping a breathing zone behind a protective barrier. It's one of the most important safety aspects of working within fume hoods. And oftentimes we go into a laboratory and the sashes are wide open because it's a whole lot easier to work with a sash wide open because you can reach everything. But there's risk reward. So having that sash down definitely keeps the safety up by comparison to having it open. And then there's also some options for annotating where on the side panel where the sash should be and putting in a sticker, as you can see on the left, or putting in physical barriers like the sash stop, which is drawn in on the middle, or automated sash positioning systems, which you're seeing a hand changing out a sensor on those so that the sash automatically goes back down to a certain position or opens up to a certain position and stays there when motion is detected. So these are options to keep that sash at a safe range, and also it works on an energy efficiency application as well. So it has dual-fold purpose, but ultimately safety is priority one. And then minimizing air turbulence. Having this hood directly next to a door, not ideal. Maybe it was the only place they could put it in that laboratory. So there are some restrictions on locations, but clearly not the best place. So keeping that door closed so that there's not air moving in and out of the laboratory frequently would be the right choice, but a good demonstration of how not to do something if possible. The other air turbulence, moving your hands around with rapid movement inside of the fume hood. Again, air isn't very dense, so it's easy to disrupt. So having slower movements while you're working within the hood is a safer bet for all technicians. Something that isn't discussed very frequently but is also important is cord management. So, because most fume hoods have their electrical duplexes located on the corner post somewhere, keeping those cords in a safe space minimizes risk of spills, of electrical disconnection, so there's application issues. Having cords laying across the airfoil or going up under the airfoil can disrupt and create turbulence for the aerodynamics, especially on lower velocity fume hoods. If you've got a bunch of cords that are tucked under the airfoil, that can change the airflow dynamics. So most hood manufacturers have some type of cord management system where you can tuck those cords in as they're entering the fume hood and mitigate risk by not having cords laying around. So it's something not touched on too frequently, but it is an important aspect of safety when you look at the overall picture. And then monitoring the face velocity. So the blue image, they're showing the actual digital display of what that face velocity or the speed of the air is, and knowing what a safe range is. Most monitors are calibrated within a safe range and will alarm. So just keeping an eye on those, and if you notice something that's not working, there's some ways to go about it. Looks like I got these slides backwards, so I'm going to skip this one. And this is an option you can do, is getting a little a visual smoke stick to check the airflow if you think there may be something wrong with how the airflow is working, and that maybe the airflow monitor perhaps is malfunctioning. So it gives you a secondary option. Again, chemical storage, not putting the stuff in the fume hood and leaving it in there all the time. That's why we have chemical storage cabinets like the acid and flammable cabinet shown in the middle. There are times where it's necessary to have these chemicals in the fume hood frequently, but obviously it's better to keep them in the proper type of storage containment so that you don't have potential risks and you're not disrupting the airflow and possibly damaging the containment capabilities of the fume hood. And if the airflow alarm goes off, know what to do. Lower the sash immediately. Make sure that it wasn't something that was accidental. If the alarm continues to sound, stop and close the sash completely and let a lab manager know if it continues to make noise when the sash is closed. There's obviously something wrong. Maybe there was a catastrophic failure with the blower. If you've got highly toxic chemicals, you want to evacuate the laboratory. There's no reason to risk your own safety or your technician's safety because of ill-advised practices when the airflow monitor is making these noises. There are professionals to come in and evaluate the situation to make sure that everything is safe. And this happens from time to time that there's either a failure in the blower system or there's some different type of alarm that's causing, or there's an electrical malfunction. So understanding how airflow and alarms work within the hood, putting that in the training processes really helps with the technicians understanding what to do when these occurrences happen. Again, improper use of hoods, putting a whole bunch of stuff in there, disrupting the airflow, blocking the baffle where the air is actually drawn up into the duct system. So now you're creating greater static pressure, which reduces the air volume. So there's all of these consequences that occur by actions that take place. We'll touch on fume hood maintenance here. Proper PPE, wearing gloves and goggles at a minimum, putting on some coveralls, masks may be necessary. Wearing the right equipment, both in using the fume hoods, but also during the maintenance process. Again, in the exterior, probably don't want to do what the picture on the bottom is and jump inside of your fume hood and start wiping it down like that. Obviously, you want to be able to clean the sash, remove the baffles and things of that nature, but there's better ways to do it than sticking your entire body inside of the fume hood. There are wands that can be used to reach up inside and clean the glass. Baffles can be removed, but again, having the proper PPE and knowing the applications that have been done within the hood so that you can properly clean it and do it safely. Additionally, if you've got equipment around the hoods, making sure that those pieces of equipment can be moved and can be safely evacuated, and just kind of having general situational awareness and knowing what's going on and what needs to be done so that you can properly maintain the hood without disrupting the laboratory area. The picture on the right shows a pretty clean lab. Picture on the left, a little bit more dirty. So regardless how the lab looks, there are ways to ensure that you can get the maintenance done properly without potentially damaging or causing a hazard or a risk. And then if you get a new hood, this is something that you should probably ask EH&S or somebody to do is go through and assume that there are residual chemicals that are hazardous somewhere. Confirm whether or not there's perchloric acid, again, because of that explosion risk we discussed before. So there are certain tests that can be done on that. But if you're inheriting a new hood, you want to make sure that it's been cleaned and validated through a certification process to test against the internal standard. And then after all of the maintenance is completed, obviously we want to bag up everything, give it to EH&S or whomever the appropriate organization is for proper disposal, and then wash with soapy water, gloves, respirator, goggles, whatever it might be. And removing PPE is important. You just want to wash off any potential skin or body part that's touched anything that may have been covered that has a hazard to it. So making sure that you're doing things properly, and again, we can work with standard operating procedures and training methods to develop how you want these processes to take place within your organization so that your individuals doing this type of application are doing it safely. So as a quick recap, is planning for safety, the organizations that give you some support and can help you devise how you want to create your safety plan, your standard operating procedures, and your testing procedures, the different hood types and how they can dictate, how the application dictates which one you should do, and designing the laboratory so that you have the right functionality for what you're doing. Knowing that we have standards as a manufacturer that we need to follow, so those are validated, verify those before you make a purchase, and then your own institutional, organizational requirements, and then the recurring certification processes, and then creating procedures, the best practices, training tools, how to understand what's happening when alarm is going off and what the steps are to work on those, and then maintenance and cleaning. So I see there's some questions that have been asked throughout the presentation, and then we will let Catherine address those, and I will wait here patiently. Thank you so much for your time. I really appreciate everything, and I hope this was useful for everybody.
Thank you very much, Nathan. And to our audience, thank you for sending in your questions. If you joined us late, please note that you can send questions to our speaker by typing your query into the question box, which is located on the left-hand side of your screen. If we don't get to your question today, rest assured I will forward it to our presenter so he can respond to you directly. This time we're going to move directly into our question and answer session. So the first question we have is, this individual is asking, what is a washdown system?
All right, so a washdown system is it's a spray system that either is attached to the rear wall or the baffle of the fume hood to condense vapors that would then be drained out through the appropriate drainage system, and there's a trough in the rear of a fume hood. So the baffle sits just off of the back wall of the fume hood. As vapors are created, there's potential for condensation throughout a duct run perhaps, and there might be dripping back down. So it's to get those residual condensations that might then dry up and sit on the baffle, on the back wall, or in the duct system. So washdown is essentially just spraying water at different periods of time depending on requirements for protocols to wash down potential, for perchloric acid, it's the dried up perchlorate salt. For other acids or other, it's mostly in acids. So if it dries up, you can wash it off without having residual dried up acids within the duct system or within the fume hood.
Thank you very much. We've had several people ask our next question. So how do you recommend cleaning a fume hood?
Yeah, it's a little bit challenging. So because the applications are working with hazardous chemicals, essentially it's start at the front and then you can work your way back. So with the wand I was talking about, you can put on PPE, soapy water and clean the back of the sash. So now after that's cleaned, and you can then wipe down with general water to basically clean off the sash. You don't have the residual soaps. And then you can open the sash up and start working on the sidewalls, working way from front to back and really top down till you can get to that back baffle. And once you get to that back baffle, you've already cleaned all of that space as you're approaching. So now a baffle can be wiped down from the front. Baffles also are removable, so those can be taken off and then just turned sideways within the hood and cleaned off there, and then getting the back wall. Again, a wand is a really nice tool to use because it gives you the extended reach without having to put your physical body inside of the fume hood. But it's good practices to go through and have a cleaning of those hoods over time. It's also going to prolong the life of the fume hood. Many laboratories have older hoods in them, so fume hoods are expensive, renovations are expensive, and by working front to back, you can clean the hood, prolong its life, and do it in a safe fashion.
On a related note, how often do you suggest that baffles be cleaned?
It's really tough because it's going to be often application-based. And most of the vapors that are produced in a fume hood are going to be exhausted single pass. It's not too frequently that you're going to have condensation occurring unless there's some type of chemical in the hood being heated into a vapor. So at room temperature, it's going to be a liquid, because along that duct run, things are going to cool. Through the speed at which those the air is moving through the duct, you're going to have evaporation and, first condensation, and then you have evaporation taking place, all within the duct from time to time, depending on the chemical. So, there's no perfect every month, every 6 months, every 2 years time frame, but just know that it's good practice to do to clean out your hood, from time to time. If you're doing a lot of, heating processes where you're changing a phase from liquid to gas within the hood, then you probably want to do it more frequently than if at room temperature you're just having general evaporation. If you're forcing evaporation to take place, that's typically where you could have more residual on the baffle or the back wall of the fume hood, because that's the path at which the vapors will leave. So unfortunately, there's no perfect answer on that. I would just say, if you're doing a lot of heating processes, you may have more residual on your baffle than if you're not. And maybe something to consult with EH&S to ask if they have any ideas on, based on your application. Clean it for the first time and see how dirty it is. And if it's really dirty, then you may want to put in a process. If there's not much there, you've got the option to prolong the duration between the next cleaning.
Thank you very much. Our next viewer asks, can you safely spray paints or coatings in a fume hood?
So it's going to depend. There are applications where paints are being sprayed, but paints are going to aerosol and then they're going back into a liquid form and eventually will dry. So you're going to likely have some of the paint residue going into the duct system. So it's going to dirty up the place. But as long as you're spraying towards the rear, and of course, right, there's going to be applications and usages that aren't the right option. But there is the capability of using these, but typically a paint booth that's designed for painting applications is going to be the right choice versus a fume hood. I mean, a little bit of spray paint on something to, as a test is likely going to be fine. But if it's actually a painting application, fume hoods typically aren't the right choice for that. We're trying to evaporate vapors and gases as opposed to painting applications that are going to have particulates as the majority, with some byproduct gases that are used in some of the spray paint applications. But from a gun, you're going to create a lot of particulate that isn't ideal for how fume hoods are designed. But possible, yes. It depends on the application and whether or not it's the right choice.
All right, thank you. I've got one final question for you. So this viewer asks, what should I do if my existing hood layout doesn't align with recommendations?
Well, as long as you're, so in those circumstances, the certification process is going to be the key to making sure that your fume hood is operating safely based on where it's located, based on the design. So, if it's located directly next to a door or there's an air diffuser blowing on it, there's some options that you have. Obviously, try to minimize the use of the door. If it's the only door entering the room, then there's challenges there. It might be increasing the face velocity so that you are having you're able to overcome adverse conditions more effectively. If the diffuser is blowing air towards the fume hood, there's all sorts of blocks that can be put into the diffuser to direct that air to the opposite direction. So you're still getting the supply air in the same volume, it's just not blowing at the hood. If it's in the middle of a walkway that's well traveled, again, face velocity changes increasing may be right. But address that with EH&S or with the certifier that comes in and see if maybe they can do some challenge tests to replicate the types of things that happen within your laboratory. So if it's within a corridor where there's a lot of walking or next to a door, open and close the door or have people do walk-bys during the testing procedures to ensure that that containment is still maintained. Because when that individual leaves who's doing the certification, the expectation is that whatever you're doing within the lab is going to fall under those same parameters. So maybe it is testing against stricter parameters so that you have the peace of mind to know that your hood is performing safely based on the location where it currently is.
Thank you very much. This brings us to the end of today's webinar. On behalf of Lab Manager, I'd like to thank Nathan for all the hard work he put into his presentation. As well, I'd like to thank Lab Conco for sponsoring this Safety First webinar. I'd also like to thank all of you for taking time out of your busy schedules to join us today. For more information on all our upcoming or on-demand webinars, or to learn more about the latest tools and technologies for your laboratory, please visit our website at labmanager.com. We hope you can join us again. Thank you and have a great day.